learn about the introduction of the complex numbers. And then we had seen that there was another way to use the complex numbers to solve just a real value function by recognizing that a complex function can be written using cosines and sines. And once you realize that, then it became fairly easy to solve what you used to have to solve using the, oh gosh, help me out. Maybe UV minus VDU.
The integration by parts.
Yeah, the parts. And you had to do it twice. But this time you only had to do it once. So today we're going to continue that idea. So we're going to solve y prime minus ay equals capital A cosine of omega t plus b sine of omega t using complex numbers. Complex numbers and real value functions. Real value functions. I think that's what I'm right. So we're going to do a warm-up to make sure you're on the right track. I'm going to give you a few different pieces today. So our first goal, this is all warm-up. Let me just tell you what we're leading up to. So our goal is to express this whole new input, Q of t, is to express Q of t as in the exponential form. That's this right, in the exponential form. It's going to take some clever trick and just a little bit of experimentation, but I think if you go through this process, it'll help you to see it and what we're after. So the first thing I want to do is we're going to have a few different numbers today. I want to start with this number, z. Remember we said z is what we usually represent a complex number with. So I'm going to write this as z equals capital A plus capital B I. And if you write I capital B, that's fine. What I'd like you to do now is take a moment and sketch that. Can you sketch Z graphically? And if you're like, nope, don't have a clue what you're asking. That's okay. I'll do it too. And then you check your graph, and I'll check my graph, and it should look pretty simple. So I'm going to make my graph like this today. So we said the horizontal axis represented the real component, and the vertical axis represents the imaginary component. And so if I have my real value is A, so I'm going to put A right here, and my imaginary component is B, so I'll put B right here. There is our graph of Z. So we can say this, we'll write it here, Z equals A plus, I'll write it this way, IB, just so you get used to seeing it both ways. So now, I I'd like you to take a moment and see if you can, and also on that same picture, see if you could plot z, the complex conjugate of z. So take a minute and put the complex conjugate of z on your graph as well. Remember the complex conjugate. Does someone remember how you find the complex conjugate? Correct. Did you all, so Hans, I don't know if you can hear that back, but you change the sign of the complex component. So what would it be? A minus bi. Correct. A minus bi. All right, so let's draw that. Minus b. Let's graph that. So this is a complex conjugate of z. Now, the next step is, let's write z in polar form. Actually, not even polar form. I saw that one. Oh, we can. Not polar form. Exponential. So in order to do this, we need to do a little bit more labeling. In order to do this, well, actually, you know what, let's do exponential form, and I'm going to write this way. I think it'll help you to see this, and polar form. So let's look at this. I'm going to call this blue line here, I'm going to call this capital R, like a radius. And there's capital R. And we need a name for this angle, so I'm going to call this angle here, be consistent with our text, I'm going to call it the angle phi. You could give it a different name, it would be the same result. So, if this is phi, what would R be? What would R be? You can find it. Yeah, the Pythagorean theorem, sure. So right off the bat, R should be the square root of a squared plus b squared. It's just as you expect, so let's write that. So we can say that R is square root of a squared plus b squared. So no surprises. And, oh, phi. How would you find phi? Did he what? Yeah, use the tangent. Notice that if we want to find phi here, the easiest way to do it, you could use this big square root, but that's kind of ominous. But a cleaner way would be to notice that the tangent is just the opposite over the adjacent. So we could also say that the tangent of phi is equal to the opposite, which is b, over a. Let's do this. Now, oh, do you remember what we said? If we also did this, we said that the cosine of phi was write that, and then we said that the sine of phi was something. So take a minute and write those proportions as well. The cosine of phi is going to be b over r. Cosine, no. A over r, good. A over r. And the sine of phi is going to be b over r. And so if we did a little bit of rearranging here, if I solve for a becomes r cosine of phi. And doing the same thing, we have that b is r sine. Let's put this all together. And I think it'll be 3 simple lines. But they took a lot of work to set up. So let's go back to z. We said that z is capital A plus I. But then we do this picture and we wrote z in a polar form. And when we did that, so here this was, we said these were our rectangular coordinates. And then we said, well, we just found A. A is r cosine of phi plus I, and we found b to be r sine of phi, and that gave us a polar form. Let's see, let's factor out the r. Now I'm left with this cosine of phi plus I sine. Why would I do that? Yeah, this is e to the I phi. And so my final step is we can write this now as r e to the I. Okay, and there we have exponential form. So that's the connection between those 3 different forms. And I think what makes what we're going to do a little bit confusing is just trying to keep track of all of these things. So we're going to do a little bit more work. We need some more identities, and we still have to figure out how to write q here in our complex form. So we're going to do that first, and then probably our second half of class we'll solve these problems, and we'll do it a couple different ways so you get exposure to how all of this works. Okay. Oh, I have one for you. I'm going to give you 10 seconds. So I would like you to write z complement, or the complex quantity of z in exponential form. See if you can do that.